Okay, we'll just wait for a few minutes and then start. In the meantime, if you guys have any questions, feel free to ask me. Okay, I guess we can start. So last session we saw about input and output IO, like essentially file IO and normal just variable IO. So we have some text we want to read from or read out or some other thing. So essentially the input and either of them use the input and output stream essentially. So that's what we saw. So the first one, if you want to use the C in and C out, okay. So those two streams, input and output stream, have this syntax where the arrow essentially gives you the direction to the code or from the code. Okay, so C in as in reading from the terminal to your variable. C out means you're streaming text or variables or strings like other things to the terminal. Okay, straightforward. Here we are reading a variable to C. Here we are outputting hello world. Okay, and also furthermore, we saw about ENDL. So end line is two functionalities at once, where it is the new line, okay, and flushing of the buffer. Okay, so those two together is the end line, right? So essentially, it's like if you keep filling the stream, okay, with some text or output, then first the buffer gets filled. When it gets filled, it gets flushed out. Then it takes in new data. Okay. But if you want the buffer to be cleaned, okay, that's when you use stand flush. Simple. Okay. And then we know this to print variables. So you can just put text like this, and then you can have variable names like this. Okay. All right. Okay. Next, we took example of IO manipulation. Okay. So specifically, let's define I to be 17. It's an integer. So in decimal form, the 17, that's the default behavior. So if you write 17, it means it is in decimal form. Okay. We can make a long. Okay. So by default, when you define something long, okay, it means long int. Okay. It's just a short version of writing long int. Okay. So long int, so it will store integers and the variable name is L, but the format in which we are defining this number is a hex. Okay, so 0x is the hex format where the digits are 012 A78CB. Okay. Now in decimal form, the same hex representation in decimal form will give a certain number, right? That's what we see when you try to print this guy. Okay. All right. So the number that this represents, okay, it is the equivalent version of it in the decimal form is what gets printed. But in memory, it will store in the binary form. Okay, everything always gets stored in binary form. Okay, it's a different format of seeing the same number. All right. Furthermore, you can go ahead and define long unsigned int. So here I'm saying it's I64. So saying that it is a 64-bit integer and some huge number like this. Okay. All right. Then the difference between F and D, where both of them are 15 divided by 7. So now, because 15 divided by 7 is a non-terminating number, and well, then again, it's infinite digits, right? So to represent this number accurately, you need infinite precision. But since we don't have that, the best we can do is represent in two formats that we usually have. One is the 64-bit format, the double format, or the 32-bit format or float. So here, printing this, we see that there's difference between how many digits you can actually comparing these two, essentially. How many digits of float you can confidently trust. Okay. Essentially precision, how precise your output is. Okay. 32 bits obviously will have less precision than 64 bits. Okay, in floating point format. Then we define a character C with the character X itself. And the hello world string, you can define as a character pointer, okay, as an S. So it's a character pointer. So S will have store the address to this hello world string. Okay. And then you can do some typecasting to store the address of S itself. We typecasting S as a long unsigned integer pointer. Okay. So yes, this address is defined as okay. Actually, s itself is a character pointer, as you can see here. Again, const character pointer, right? But you can typecast it and then store this address in other formats, right? Another straightforward thing one can do is store the address of I that we have defined here as an integer pointer. Okay. I is an integer, you can store its address in an integer pointer, right? Okay. Then you can, yeah, here we see the same, some more examples of I. So I itself by default is in decimal. You can print the same number. Okay. So 17 is in decimal form. You can force it, force your output to have hex format. So you can do that using standard hex and using standard oct, the oct format. Okay. And yeah, L here would have printed in decimal format. So that's again, so hex format you can also choose. You'll see the same answer here. Okay. With I64, similarly, you'll see the same thing, same number in decimal format, and in hex, you'll see the exact same string. FND again, those things. And yeah, now comes the IO manipulation header. So we included this header to use the set precision function, okay, where we want to print more digits than are printed by default. Okay. I think by default there are like 5 or 6 digits or something like that. So we extended it to 10 to actually compare at what digit do these two numbers F and D differ. Okay. Right. So yeah, so F and D differ. And from that point, you are uh, sort of assured that at least F is not as precise as like till what digit it's actually precise, right? Even the double format also has precision till certain digit. That is also there. But yeah, then again, that's this basically showcases that difference, that one is more accurate than the other. Okay. And you can print all this other stuff that CS addresses and sorry, CS and addresses and all that. So to compare the address number itself. Okay. All right. Then we take an example of actually using friend class, right? So we're using a, sorry, not class, friend function as part of a class where we actually overload the stream, the standard stream, essentially. More specifically, the standard output stream. Okay. Why do we want to do that? Because by default, when we have, let's say, a custom defined complex number like this, the IO stream is not familiar with how to deal with these objects. Let's say we want to print in certain format like this, right? Using brackets, the real part, comma, imaginary part, and then brackets. So if we just put C1 like this and C2 like this, ideally it will not know what to do. Okay. So there's certain modifications you can do. Okay. So that the standard output stream now gets extended to this format also, where it not only just takes standard output stream OS, okay, usually it has certain defined inputs like integer, float, double, and etc. etc. But now we have extended that definition. You can think we have overloaded it, okay, to taking even standard complex. Sorry, to even taking uh, complex class like the user defined class like this. Okay, so that's essentially what happens here. It takes the stream that is running. It takes the complex number also. That's essentially what is happening here, right? And then it returns with this formatted real part and imaginary part, and that's it. It adds it to this stream and then returns that stream. Okay, straightforward, right? The reason to make it friend is that now because when a certain function like this is friend, that function is accessible outside the class, right? And it can access the private members also. That's actually the reason the friend was needed to be made. Okay. And yeah, that's it. So I can use this new added function to just print C1 and C2 or any other object of the class complex as you wish. Okay. All right. So those were how to manipulate the streams, IO streams, right? Now coming to the file manipulation, you specifically need the F stream. Okay. And yeah, so the typical syntax looks something like this. You create an object, my file of OF stream, so output file stream, right? So using the output file stream data type, you create a new object and use the method or the member function of the class open. So you open that file, let's call it test.txt. So now that file uh, is created if it's not there, okay, and it's opened now. And then to that we write all this text, okay, and then we finally close the file so as to free the file for it to be used by some other process or something else or other code or anything, right? So it's a good practice. You open the file and then close it. This is the clean way of doing this. Otherwise, the problem that can happen is the file is opened by something, and let's say we are writing here, right? We're changing the data, and some other process also comes and writes to the same file. Then you have a race condition where data is getting overwritten, which is more or less never we want to happen. Okay, right? So good practice. Open the file, write to it, and then close it. Okay, and then last example. Yeah, right. Yeah, it's if IF stream, so input file stream. Where we're reading the actual text file that we created before. Okay, and we're using the string header to define the standard string, like basically access that, and define an object called line. And we're using that line object passing here with getLine. GetLine is a C function. Okay, so you can use my file as the input where you're taking the F string, and the line will be inserted each line that we get inside the file. Okay, so getLine takes care of that. It goes through each line separately, puts it inside line, and then that's what we're printing here. Okay, and it keeps going until it cannot get any more line, and that's where the while loop ends. Okay, all right. I hope no questions so far. Okay. All right, let's start a new topic today. So first of all, type ID. Okay, I'll create this. First of all, let's include IO string. And have the main function. First of all, integer. Then let's say it's not integer. Some double D B. Load C. So A, B, and C. And again, C is a strongly typed language. Okay. So whenever declare any variable, the type or the data type of it has to be known at compilation time. Okay. You cannot have it like, oh, it will be some variable later on, some other memory. Reason being that it can optimize storage. So that is hard coded by the standard. You can think that way. Now, because of this, can I know the data type of it by like a query? because it does not change, right? So if I have ABC defined someplace, I sort of won't remember. I mean, I have to just query it for to check something, or maybe something else. Okay, so maybe the return type changed or something else, something happened. Maybe you used macros, and depending on compilation, your A and B will have different um, data types. Okay, due to certain macro. And let's say you want to query and you have some branching statements, which like if and else statements type. Okay, which depend on the data type of A, B, and C, right? So, is there a way to actually know what is actually the data type of your um, variable? You could make your if else state like branches also under if there's probably, but that might be too much because sometimes you just want a certain place to have macros and rest everything follows from it, right? Like plain old simple C++ code without a lot of macro confusion, right? So turns out there exists a way. So let's do that. So let's say I have A. I'll make it this way. So it's I'm saying A is data type. Okay. So you use something called type ID. Okay. And type ID, but let's say yeah, it takes the object and use the method called name. Okay. And the function. That's it. So that takes care of printing what A is. So let's print this. Okay. Right. So that's set ID. Right. So it prints I. Okay. Uh, what does it mean is it's actually saying A is integer. Okay. Let's take more example. So let's extend the same thing. As you can see, it says D, as in W. Okay. And C further prints F. Okay. Right. So depending on what data type you have, maybe in a certain part of the code. So if it's A is integer, you maybe want to go through a certain path, right? But it's something to be aware of. Okay. Even if it's not, maybe you'll not use lot of often nodes. Yeah, right. Now, next one. Um, So I've been saying that while C++ is a strongly typed language, right? It is possible to write a code very Pythonic like. You can have C++ look like very much like Python. In the sense, uh, it might seem like you don't care about data types and something just works, okay? Where auto comes into play. That's exactly where auto comes into play. So let's take more example to see what I mean. Okay. But it might seem like we're writing Python in C++ because of the new standard. Do remember, it is still a strongly typed language. That has not gone away. Okay. It's just that it's more abstracted out, which these new features provide. Let's look at example to understand this statement a bit more. Okay. I'm saying this because you have this in the back of your mind. Okay. And yeah, I miss this header file called map. So main. Now, let's say I define auto x. Okay, and I could have defined it as integer x or some other data type, right? Let's say I define it as in auto x. Okay. Now, if I just were to just compile this code, right? Is there a way for the compiler to know what x is? Like what kind of storage it will have? Any guesses? I'm saying auto is sort of a replacement for anything. Okay. Where auto just determines the type. Okay. Now just think about it. You want the compiler to still have the knowledge of how much memory should your variable take. That much memory it will allocate. But if I just have auto X, can it do that? Any attempts? I'm
Hello.
not able to hear. Yeah, I'm not able to hear. I think, yeah, try again. Yeah,
So
go
what
ahead.
I'm saying is if we initialize this auto to x, let's say x equals to 1, then it can infer that the type is of integer. If we can define it like 2.5, then it can infer it's of type double.
Right, that's correct. That's where the motivation lies. If we just have auto X, that's correct. If we just have auto as X, then it does not know and it cannot compile this. So this actually, if you try to just compile, will throw an error. So let's just check that. Okay. So that's what the error is. The declaration variable with reduced type auto requires an initializer. Essentially, what it's trying to say is, if you try to initialize it with some variable, like uh, as the answer was told. So if you try with 1, okay, then it knows that I have to store the number 1, okay, an integer in X. By default, I know how to store it because the compiler knows. This is what compiler is saying. I know how to store this. So I will reduce its data type. Okay? It's compiled. And the good thing to know is, let's check the data type of X because now we can using this. So let's do that. Okay, that's an integer, right? That's what we expected. Okay, and that's what it is. And let's say it is 2.1. You cannot declare it twice. You can redeclare the same variable. So you have to comment that guy. So let's say if it's 2.5 times double. Yep. All right. Usually it is very conservative in the sense you'll try to use the higher bit to represent the number so that, well, things don't uh, like it tries to reduce the data type and then use the max sort of the maximum so as to represent it and so that you don't run into issues in storing this value. That's what I'm trying to say. Okay. Now let's define a data structure for standard map. Okay. So essentially it is a special data structure. Okay. A standard map is essentially a data structure where you store key value pairs. Okay. What does that mean? What it means is think of standard vectors, okay, or the list data structure whose representation is standard vector or standard array. Okay. So specifically, think of the abstract data structure list. So we know the starting address and there is a contiguous memory layout, right? And the 0th position stores some data, first position stores some data, so on and so forth. Till some maybe n values you have of the data structure. So the data structure then stores some n values and you have some n values stored in that abstract data structure. What happens in standard map is instead of, so there also you sort of have a map. So 0 is mapped to some value, 1 is mapped to some value, 2 is mapped to some value, right? In standard maps, pretty similar. You have some keys which map to some value. You can think sort of the list data structure to be a map in a way, but there it enforces certain more rules like data contiguity and the key value pairs have to be with integers, right? So the keys have to be integers, and then there is a contiguity in there. In standard map, the abstract data structure does not put any such restriction. You can have a key to be not just integer, it can be any immutable data type. Okay. When I say immutable, any data type which cannot be changed. So let's say you make a const integer, like you can specifically distinguish those data type from one from the other. Okay. So like the numbers itself, one is different than two, which is again different than zero, right? So once you have a certain uh, data type which is satisfies the rules for immutability, like integers, then you can use those data types as keys. So standard map hence work with this principle where there is a immutable data type which is keys, and the value themselves can be mutable. It can be any value. You can even map any uh, object of a certain class, like any instance, like let's say every instance of that object as part of a as values, and all of them are mapped to certain key in a map. Okay, so that's what map data structure is, and C++ gives you the representation of it in the standard template library called standard map. Okay, so to use such a map, you have to have it's also a templatized class. You have to have two template parameters. So the key and value pairs. So it defines the data type of them. Okay? So what is the uh, data type of your key? What is the data type of your value? So let's go with both being integers for now, and we'll define the object as map. Okay? Straightforward, right? And let's say I want to define the um, I want to sort of iterate through this map now. Okay. The standard way of iterating through vectors would have been to write a loop, right? And since I know each data is contiguous, right, I can start from the starting address of the pointer. So I can then do the bracket operation, a of I, and then I access the ith location. It's pretty straightforward, right? But that works because it is contiguous in layout. But maps, as I said before, they need not be contiguous in layout, right? So we need something more general, which we can use to go over every element in the data structure, a much more general idea. Okay. And that's where iterator comes in. Okay. Iterators are essentially this. They are more general. So basically you want a certain way to go through every element in a data structure. And as such, there is a way to do that, which is iterator. And now the thing is, iterator is defined specifically for every class separately. So like the standard map has its own iterator. Standard vector also has its own iterator, and so on and so forth. Everyone has their own iterator. Now, because of that, the syntax of it looks something like this. So you need to use standard maps integer. Uh, Now this is the template. Okay, specifically this is the class name. You can think that way. And in that sort of the namespace, we use iterator to tell that this is the data type of my whatever object I'm creating. And the object, I just call it as begin. Okay, where the object that we created with the standard map, okay, with the capital M dot begin is what it will return. So dot begin is the function. Using the dot, we're accessing the function begin, and its data type is essentially this. Okay, I hope this is clear because standard map integer is the class name. That's what we used here. The class name is itself used as sort of an namespace, right? So that is the now the data type. So with double colon iterator. Okay, and map begin is the object which stores this map dot begin. Right now, yes, it gets a little bulky. Yeah, and but let's use that. Okay, and write the complete loop. So, we'll have standard map, integer, taking with the iterator. Let's call it iter. Okay. Starting. So this is the integer I equals to something, right? So the equivalent is like we define the data type. I is my iter, which will keep updating. Starting, and then we have to initialize it. So we'll use the starting begin. Okay. Right. And then made a stop condition. So until iter equals to, oh, sorry, it is where this more cleaner. Until iter is not equal to map.end. Okay. So when it is actually map.end, then it will end. Okay. Right. Until then, you can just do plus plus. That is okay. So this iterator has this built-in plus plus to understand. It is sort of incrementing, but not by one. Okay. It's sort of there is an increment where it will make sure that goes through every there's a starting, there's an end, and there is a process in which there is it will go through every element. And what is that specific order? Again, that depends completely on the map. Okay. So with this for loop, now you can access uh, the maps things. So the standard map has key and value pairs, right? So to access any element, you sort of so it you actually think of like a pointer. So we're using the arrow operator. Okay. So the first element is accessed with first. Okay, so that is public. You can actually access that member. Okay. And you can just give a comma with space and then access this second part of the iter with end line. So we wrote the whole thing, right? And yeah, this is something you will encounter quite often if you use maps, right? But what if we now use auto? So in this case, let's write the equivalent here. So I can just put auto map begin equals to map dot begin. Plain straightforward, and I do not need to worry about what is the data type of map begin. It's sort of understood that I'm starting this map begin is my starting iterator for my map. Sort of understood from the variable name. And the data type is known because of the return type of map.begin, right? And you could get comparison issues, and if you're not from being specific with whatever template you have given and so on and so forth, right? It is possible you might want to hard code it here, right? Or sometimes it's just cleaner to actually just use auto. So essentially, because in C++ we do have very long names like this, right? It's a good example where you do not need to actually follow um, like writing everything specifically. You can just leave to the compiler to um, get it done. Nonetheless, here in this specific example, it's sort of clear as to what we want the intention of the code is, right? So it is okay and allowed. And if we say something like this, where the for loop itself gets very confusing because the map.begin, the iter sort of hides here behind this uh, data type. And then we have the map begin and iter does all its job, right? So just using auto here also makes it quite clean. So I can just have auto iter equals to map.begin. Again, pretty much straightforward and understood, right? Same thing here. I'm just using the iter here and have iter not equals to map.end and make a plus plus. Okay. Fancy out. Now to print them and straightforward just go with iter first guy, comma, iter second, and then end line. Okay. The map begin starts my map begin variable pretty much similarly as before, but now I don't need to worry about the data type because it's being taken care of by the compilation. I'll not compile because runtime will throw errors. I'm not initialize the data. Okay, so this will actually this should be okay still running it because if you don't initialize it, the end should not print anything, right? So yeah, to take care of it. So the only the print that you get is from the XD. All right. So comment. Right. Any questions of what? Oh, question is usage between template and auto. Now the thing is you can think of it this way. Both are different things, okay, but both are compilation time. No. While template itself uh, defines what your class. Okay, so if I go back, so if I take this example, so templates define what my class or my function variables will have, what data type will they have. Okay, so if I take this example, or maybe a simpler one, no, this is macro. Okay, this is fine. So if I take the max function, so now here in this case, my template, if it is double, so all my variables were starting from the return time to input data types, all of them are double. Okay. So I can write many code together with this. So just a second. Okay. Yeah, like I was saying, so with templates, you can decide what your function data type, all of them will look like. Okay. What auto does is it defines the data type for your variable. That's it. Now, nothing stops you from saying you can actually use them together. So if you see, I used auto here and I used templates here, right? Because templates are known at compilation time, okay, you can actually pass that on to furthermore. So like, for example, if I use template like this, okay, with TA and TB, and the body of the function has, let's say, the standard map, and I can make both of these as capital T. That's absolutely allowed. Okay. So that's how templates can propagate their data type. Okay. You can actually go ahead and make it integer, like using from type ID also, like you can use certain operations and then make it return integer. You can do that. Okay. Now specifically auto is known as completion because of the right hand side value. Okay. So if we have a initializer, okay, so here specifically because x is initialized to 2.5, so there is an initializer. Okay. Because of that, the data type of x is known. So that's when you use auto. You can't use template here. Okay. Templates are meant for more specifically functions and classes. Okay. Subtle differences, but you can use them together. You can actually make things auto here also. Okay. If the right hand value side is known. Okay. That's how auto works. But templates, they also sort of inferred. So let's say I put integer here. So everywhere I have t, okay, is now used as integer. Like integer is inserted there. Okay, is that clear? Okay, good. Right. Okay. Right. Any other question? But you can then move on. Okay. So, X has its known data known at comparison time, right? So, what if I make another variable y, okay, and let's right hand side be X. So, what's happening in this case is I know my data type is of X is something. I want to store the same variable in Y. So I should be able to propagate my data type of X to Y, right? So I technically I can use auto here. Let's see that. Okay, that's working. It just prints this guy, of course, but let's try printing Y2. So if I print it, so both of them are double. It works because the data type of X is known at comparison time because of the initialization. Same with Y. Because of the initialization, you know the data type of Y. Okay, so auto works here. Now, another important thing, what if I want to define const auto? So if auto is integer, what about const auto? It's also double. What type ID does is it takes the base data type. The extra qualifiers like const and other things that it does not pick up. Okay. So, but it should also tell you something else. Auto also picks up the base data type. We'll take more example in for this, but keep in mind if X is integer or double, you use auto to get that data type only. The other qualifiers, you have to be more specific and declare it on your own. Let's take more examples, it will be clear. So, const auto, you can even define pointer y. As I said, since this one will not work because, oh yeah, I just stored as a x. I need the address of it. Sorry, my bad. Yeah. Okay. So that's PKD as in a pointer. Okay. With C. All right. Now, what if we make it a reference and pass x? Okay. This case is just D because the data type auto of y will be double, right? So double reference will take x as it is. Only for pointers, it would have taken the address of x. Okay, that's it. Okay, let's take another one. So let's have the main function. Now let's say define A and a pointer B. Okay. What does now we saw the limitation of auto. It only takes the base data type. So if your X is integer, auto only picks up integer. Okay. And if you want to define Y as a const, it has to be known separately. Like you have to explicitly define. Same with pointers. You want it a const pointer, you have to define it as const. And if you want it as a const reference, you have to declare it as const reference. It only takes the base data, integer, float, and so on and so forth. Okay. That's what we see. And that's what even type ID picks too. Like essentially what auto picks. Okay. So all right. But let's say we want it to pick even the extra qualifiers that we have. Let's say the pointer notation. So there's a specific keyword that's called the decal type. So use decal type of A, okay, to define B, right? So B is the object and the type is returned by the decal type. And decal type of A itself will take, decal type itself takes the input as A to return whatever is the data type of A. All right. So now B is an integer because A is an integer, right? Now decal type of P I'll use to define Q, where Q will be integer pointer. So the good thing about this usage is that you can get the sort of the exact data type extracted to make your variables or to declare your variables, which auto cannot, right? Okay. Let's take another example. Okay. Digit A. Let's say it is 10. So here A's data type will be integer. Okay, straightforward. Now let's say I define integer B. So this time reference taking A. Okay, so what is the data type of B? Any guesses?
Int.
Yes, but you have to be careful. It is more specifically an integer reference.
Yep.
Because yes, the base data type is integer, but if one thinks about it, the more complete data type will be integer reference. Now if I make const int C and let's say call it some number because I can't use A because it's not const. Let's put some specific value like 11. So here C will be any guesses?
Constant.
Correct. Next, let's complete the whole sequence. I can make a reference of out of constant and also use C because C itself is a const. I can make a reference out of it. Okay, so D will be const int reference. Right. Right. Now I'll make auto, use the auto A as the variable name and put A. Right. Auto, auto underscore B, scores B, auto, auto underscore C, source C, auto, auto underscore D, source D. Now what happens when we write the same thing? What is the data type of auto underscore A?
A and C is of type int, B and D is of type int reference.
Okay. Okay. Good guess. So auto B will come to this, and C is so something. B. So right. We said A and C are int, right?
Right.
Okay. Uh, but that's because I'm guessing const is extra qualifier, so we did not take that into account. And auto took the data type of A, which is already int. So that is, I think, clear for everyone. That should why it should be int. But for C, const is extra qualified. So uh, sure, that is so auto should pick only integer. Makes sense. What about B and D? So it said it's integer reference, right?
Right.
Yeah, unfortunately, that's incorrect. Reason being, pointers and references themselves are also, you can think of like more qualifiers. Okay, like const. And auto does not pick on that. It only picks on the base data type. Okay, so because your B here is of integer reference data type, it only picks integer. Very similarly for D. Whilst D itself is a const and a reference, it only picks it up as to be an integer. Okay, so that is the sort of short limitation of auto. Okay. Right now, uh, okay, next is
So, sir, we can say that the auto inherits only the type defined by the language.
the
Language
base
means,
data.
yeah,
Yeah,
base, only the
yes,
base ones.
yes, that's correct. Auto only inherits that. Yes. I could actually do this. So let's say I change B to 1. Okay. So now actually you can check this out. Uh, so B is a reference to A, right? So if I change B, A should change, right? So if I'm changing B to be 1, where A was 10 before, right? And auto underscore B, which takes B again, right? Also to be 1. I can do these two things and then check the output. It's essentially a verification of what I mean, I did claim this to be true, but does that actually happen, right? We can actually check it by printing. So let's say I just print A. Let's comment everything and let's just print data type. Do you not print this? Oh, okay, there's nothing to print. Oh, so A is 10. Uh, everything commented out, and these things don't really affect anything. So A is 10. Now, if I change B to B1, now B is a reference to A, so A should also change. Let's do that. Now A is also 1. Okay, that is straightforward. Now, if I try to change, oh, now if I try to change auto B to B1. Now, because auto B is B, and let's say your auto B inherited a integer reference as the parent data type, not just integer. Okay, then it would also change B because you're inheriting B. So if B is an integer reference and auto B is also an integer reference to the same reference, which is A, so this should also change A, right? Right? If you print it, it prints 10. It did not change A, it kept it as the original value, which means your auto B is not a reference to B. Okay, that also confirms the behavior of auto where it only takes a base data type. Okay, we can do a sort of a similar check also with C, where let's say I take C equals to 2. This is not possible, right? I was just waiting for anyone to point out. Anyway, so this is not possible because we already declared const integer C to be 11. So C cannot be changed. So this is no go. Okay. But let's say you go with on C, auto C, which takes C as the input, right? And let's say I change it to that to be 2. Will I be able to compile this?
Yes.
Okay. Okay. Yes. That's why the distinction of the different behavior of auto lies, different as in the same behavior in all these cases lies, that it only takes the standard data type or the base data type. Everything else is just a qualifier for it. Okay. I can just print C2. Right. And if I just print this, now auto C is 2 still because I just declared it to be 2. C, while it is 11, it did take the data type of it and maybe the value of it also. If I did not have, if I hadn't set it to 2, it probably would have taken 11 only. Yeah. So it also took the value of it, but not the complete data type, which is of const nature. So my auto C is just a plain old integer, which we're storing 11. And when I set it to be 2, right, it's it takes it changes the value to 2. And we check that the C value always stays 11. We cannot change it anyway. We can try, but uncommenting this line will throw error. Okay. All right. So yeah, to declare using auto as in reference or const or anything, the correct syntax will be something like this. So auto reference, you have to use a variable with A. So A's base data type is integer. So variable will be an integer reference. Okay. So notice the difference. Here, auto was simply used, right? Without anything, any extra qualifier. But if you're using extra qualifier, you will have integer reference. Okay. Similarly, you can make const auto reference add 2 or something as let's say B. I don't have B. Hey, let's keep it A. That's fine. So your var2 is of data type const integer reference. Okay. All right. So you can define different variables of different data types with auto, but you have to extra qualify it always. All right. Remember that. Let's say you do not want to worry about that and just take everything together. That's exactly where decal type comes. So pretty much the same thing, same lines, but we'll use it little differently. So decal type A takes returns the data type. We'll call it decal A. as storing A itself. Okay. Legal type B stores decal B, as in that's the variable name, and stores B. Decal type C, decal C equals to C. Decal type D, decal D stores D. Now, if I ask you guys, what's the data type? So here, decal A,
Int,
okay, then decal B,
integer reference.
right? So yeah, this is the original thing. I maybe have to, so, yeah, that should work. Just pause on. Okay,
This one is constant int.
constant.
Then constant int reference.
Change reference, that's correct. Right. So all taken care of. That is the main difference between auto and decal type. While decal type itself takes the exact data type of your variable. Uh, yeah. Uh, Auto does not. Okay. Auto just picks up the basic data type, and you have to it's on the user to actually provide the exact data type. So like here, we had to define auto reference. So then it picks up if it's an integer reference or anything else, and a constant integer reference if it's like something like if it's constant integer reference something like that, then you have to define it as const auto reference. Okay. With decal type, you don't have to worry about anything. You just take the data type of it, declare any variable, and let's say the same variable you're initializing with. Pretty much straightforward. This will work, and these are the data types that we uh, go with. All right. Okay. Compiles and all good. All right. Okay. Yeah. Another thing one has to be careful with. So let's say you have an unsigned int. I'm being very specific with the data type right now. So it's let's say it's an unsigned int E, which stores the value 12. Okay. Now let's say I use decal type of E. Okay. So decal type of E is known because data type of E is known, right? To define F, okay, right? But I don't store the variable 12 or something. I store, let's say, minus 12. Okay. What do you guys think will happen now? Is this allowed, not allowed? It'll work, not work,
I think it will work, but it will not store the sign.
okay. So that's actually correct. Yes. Do you think it will do something else too? As in that's correct. It will not store the sign. Again, reason being,
It's of type unsigned.
that's correct. So unsigned integer by definition cannot store sign, right? But let's say I use unsigned int data type, like data type returns that, right? And store from the right hand side, I store minus 12. This is the example. It is the reason I am giving this example is it's possible you can run into errors and issues. So you should understand what does this statement even mean, right? So do you guys think anything else will happen? Will not store it. So do you think it's a compilation error or runtime error? No error. It's all good. Okay, so I can maybe go step by step. Let's try compiling this. Do not throw in error, right? So at least compiler does not complain. Okay. So what do you guys think? It's a runtime error? Okay, let's run it. Okay. Now here's the thing. It not throw any error. Rather, it actually printed a some number, right? Now, unsigned integer can store values between 0 to some large number, right? And we are saying that particularly we're interested in storing 12. So that's for E. Okay. Now, decal type of E will make sure that F's data type is also unsigned int. No question there. Okay. I'm sure. Is there any doubts in that? I think that's clear, right? When we're saying we're storing a negative number -12, okay. So this is some there's a certain behavior of, you can say C also, C and both C and C++, that when you cannot store negative numbers because of the unsigned nature of your variable, it actually wraps around. Okay. So from 0 to some large number, it would have stored some uh, any value, right? But when you go -12, it actually sort of goes left and wraps around from the largest value. Okay. So hence -12 actually refers to a very large number in unsigned int cases. So this particular thing has been a source of error in many uh, cases, even gaming. Okay. So yeah, just something to be careful and aware of. So you do not, and stuff like this don't actually throw an error. As you see, it did not throw any error during compilation. It did not throw any error during even runtime. It actually just executed. Okay. So yeah, something to be careful of. And yeah, just know about it. Okay. Essentially, I'll repeat, -12 is not -12 in itself, as in the number. In unsigned integer setting, it is wrapped around from the largest value and goes to a very large number. That's sort of the idea. Okay. Right. But yeah, that's the uh, thinking towards this argument was correct. It's an unsigned integer, and yeah, your F will also be unsigned integer. There's no question about that. Decal type makes sure that the return data type is unsigned integer, and because of the syntax, F is also unsigned integer. Okay, and yes, uh, by definition, unsigned integer cannot store signs. Okay, and the example.
Sir, how does type def behaves? Does it retain the qualifiers or it doesn't?
Oh, so type def itself is sort of a generic type for any type. So if I take example, like type, okay, type def is sort of similar to type name here. So if I take about type name, it just says that I can take any data type that I'm qualified to take. Any, let's say, any defined data type. So for example, built-in data types. If it's possible, I can even take class. So you can actually define class as itself as a data type. So class is written here. You can actually define templates as class also. Yeah, that is also sort of allowed. There are more nuances, like more differences between those two, but for that you can look it up. I'm not remembering exact differences, but certain cases you can do that. Yeah, this type name, type defs, class, event, these are more general, like it's like defining data types with its own, saying that the data type if itself is a object, what should be my data type for those collection? That way, we use, in that sense, we use type def or type name, class. Yeah, right.
Okay.
Yeah. There will be subtle differences. Top of my head, I can't remember them. Okay, initialize a list. Usualize strings, and then I'll start by the main function, which yeah, let's call it an init list. Will be standard uh, initializer list. Okay, and initializer list itself is a it's actually a member of the HTML library again as a class, a template class. So you have to define the template as in the data type. So init list is a collection of some objects very similar to a vector, but not a contiguous data type kind of structure. It's just a collection of some numbers, let's say. And those numbers are, let's say, 5, 4, then 8, then 10, then 56, like that. There's no particular pattern to it. So, no pattern to it, it's just there. So if you define any square curly brackets like this and define some range of numbers, that collection is a initializer list. And I'm using the init list data type to define this. You can use auto here too and define everything like this. Just using auto. Because the template says in integer, right? And also enforces that all the initializer list have to be integers. So as long as that holds, it knows what initializer list you are actually trying to initialize. Right? And because you have the header file also. Okay. This is the syntax with the curly braces to initialize a list like this. I initialize a list where you do not want to specifically allocate memory and then go and store values. Let's say you just want to declare a collection of some values. That's it. Okay. And some more examples of auto, as in how do initialization works. So this is an initializer list. And with auto, we have seen that it depends on the initialization, right? So you can initialize, I am going to use that word a lot, sorry about that. But to initialize A, this is something we have seen before. So you use the equal to operator, okay, to set the value 1 to A. And because the data type of 1 is known, the data type of A is known, right? At compilation and auto works. So this initialization works. And the data type of auto is integer. Straightforward. Furthermore, we can use auto in this case too, where I'm using P as a function, okay, or more specifically as a class to initialize the object B, okay, with the input I as the constructor takes the value I, sorry, 1 and returns and this is and stored in B. You can use integer itself, which is auto, as the class name. Okay, so this is also a way in which initialization can be done. So I can set B to be 1, okay, using the brackets like this, where B is sort of treated as a class, okay, and the value 1 is taken as an input, and the constructor sets the value to B itself. Okay, it seems little hand wavy and not very standard, but it sort of works. Okay, this is sort of how it's defined, and it is part of the standard. Okay, because of all this, now my return is um, the object B, right? So that is what my B is. So because it is set to one, now auto also gets to know what is the data type of B. Again, integer. You can also define another way. So you use something like this, let's say, A, let's say, okay, one A or anything. Now here in this case, okay, I'll type for reference A is integer. In this case, B is also integer. Remember, equal to operation and bracket operation both sort of set the value to the left hand side. Okay, slight difference. You cannot write, let's say you define A to be some value, right? Okay, this is something you have seen in classes before. So class definitions like not this. Yeah.
So one is copy assignment operator, and the other one is regular constructor initialization.
Yes, that's correct. Yes, that's a technical term. Yes. So going to give you guys an example of this guys specifically. You have real. You're using the copy assignment to define real to be underscore real, and you can use equal to operations later. I don't have any example here itself, but it's okay. You can take example from here. Yeah, that's correct. Yeah. So don't get confused with these two syntax. So here I use this small bracket syntax to say we are actually initializing B to B1. That's essentially the idea. But here C is initialized to A, right? But because of the bracket, C is actually initialized and auto picks up on that. And yeah, it's integer because A is integer and A is one. So yeah, that's it. That's the so C behaves like this basically, but with one guy. So instead of four elements, it just has bracket one. Okay. Yeah, I think that's more or less it. Yeah. Okay. Any questions? I'll just put all the files here. First of all, type ID, then auto, data type, and then nation as a list. Yes. Okay. That's all for today's class, more or less. Next class, I'll be starting about lambda expressions, another very important concept about C++. So yeah, we'll do that next session. Yeah. If you guys have any questions, feel free to ask. Else, yeah, you feel free to leave then otherwise.
So the next class is the last class for this series, or there will be more classes?
Oh, next class will be last class.
Okay.
12 weeks. So yeah. This time I'm
Okay.
not taking any extra class. I'll
Okay.
cover. Okay. In that case, as I'm thinking, I can maybe start some of the lambda expression today itself then. Yeah, then I can cover smart pointers also, but why not? Okay, let's do that. So, okay. So lambda. Maybe I'll cover only few examples. So rest of them we can cover next class. Lambda expressions, right? So usually we'll require the IO stream as usual. So let's say I have a constant integer m. Oh, thank you. Yeah. Yeah. Let's say I have a constant integer m. Uh, Then let's say I want to write the remainder function. Okay. So essentially it's like you divide an integer by some other integer. And what is the question and remainder, right? So let's say it takes n as the number to be divided by with and returns, let's say, n percentage m. So we fixed m, okay. So the number, the divisor is fixed, which is 10. I think it's called the dividend. So the left hand side basically, what we are dividing with, that varies depending on the input to the function. So that is, let's say, n, capital N. Now, the main function you can write like this, where cout remainder. So remainder function, say it's 15. I want to divide it by divide 15 by 10. Okay, so the end line. Okay, so now let's compile this and run. So we'll have this one we need number. So it is 5. That is, I think, obvious. We divide 15 by 10. The remainder. So this is a remainder function operator. It divides integers and returns the remainder. Okay, so the remainder function then returns the correct value. That is 5. Okay, I think this is fine. Okay, you can achieve the same idea in another way. So let's look at that too. This all will motivate for us to use lambda expressions, lambda functions. So yeah, let's do that. We'll use a struct this time called remainder. Okay, where okay. Did I just a second? I'm just sure that all them are formatted the same. Okay. Yeah. Uh, I have the sorry about that. Oh, yes. The type right. Okay. So I define the same m, okay, but as a private member now. Then define the remainder function, okay, which takes itself has some m. This is the constructor, okay, and we set underscore m value with m. No, constructor doesn't need any body for this, so that's okay. Now we'll make the operator this return as the operator which takes integer n. So the operator bracket itself, okay, returns an integer n in an integer and takes the value integer n. Okay, and what will be its body? As we saw before, return m percentage n. Write it more freely. Yeah. Okay. And this ends my remainder struct. Okay. Jimmy, I can define a struct called with the name remainder, and I'll call it rem. Okay. And remember, I had set the divisor m to be 10, right? And here I made it as a private member, which is taken by the constructor. So I'll pass 10 here. Okay. And let's see out. So the remainder goes as rem. Now I'll pass 50. Remember, here is the constructor taking the value. Here it is the operated bracket which is getting operated on. So hence you see the color also is little different. Okay. Here it's the object taking the constructor. Here's the object calling the function, which is the bracket. Okay. So now if I end, that should work too. So the previous case, lambda uh, printed 5. So lambda 2 true should do it same. Okay, so 5. All right. Okay. Now, if you think about it, both of these have some similarity, as in, of course, they are calculating the remainder, but they do it slightly different way. Here I use just a function and a const member to define this. And this one actually need not be const, but then again, let's keep it that way for now. And here I used struct. Okay. Building on this, let's define something called counters. So let's define a class called counter. Okay. Define a public member operator bracket, which itself takes, let's say, general, and the body is return, let's say, n plus 5. Okay. Integer operator. Now square bracket. Okay. In integer. Now let's say that returns n plus 4. The third one, let's call it an increment. Now is the actual function itself name and return n plus 1. Now I'll have the functors ready. Okay. So the functor is essentially a function. It's actually a class which behaves like a function. That's what a functor is. Now, how does that happen? Okay. So, the functor class is the name of the data type. So I did that here. Func itself is the name of the object. Okay, so that's here. It does not have any constructor explicitly mentioned, so the default constructor is used. Okay, so I don't need to worry about that. What I'll worry about is what I'm going to do furthermore. So I'll use functor that will print using bracket. Okay, something which will be func using the bracket operation. Let's say 5. Okay, and I'll end the line. Okay, next I can use the square bracket too. There's nothing stopping you from using any of the um, brackets like this. So they are all operators in a way. You can define that this bracket will behave as operator, this bracket will behave as an operator and return this. You can, that freedom is there and you can do it. So here same, I'll use the bracket like this. Nothing stops me. I can absolutely do this. It's not standard, yes, but nothing stops you from doing this. So usually functions take data types using the small brackets like this. And if you think about it, here it's an object taking the same thing, right? That's what we did here also. The rem is an object. During construction, it does take an object. That's okay. But usually functions actually take objects and return something, right? In this case, the bracket operation is the operator and returning an integer. So you use the object with its bracket operators to take data type and return something. So here it is a functor. Okay. So we can define objects to act like objects of some certain classes to act like functions. Okay. So that's what a functor is. You need not stop it there. You can actually define it. It's not that the behavior looks like a function. So hence we are able to do this. But that same behavior is happens because you are able to define operators like this. So you can extend the same idea, okay, to even square brackets. That's what I'm trying to say. Okay. And that does not mean that the functor is not a function. Let's go to print increment. Okay. So functor, now I can use the increment and put 5. So increment is still a function and it takes values n. So I can pass a 5 here. What I'm trying to say is the behavior of function of objects of certain classes still retain their original behavior that they can call functions. That is still there. But furthermore, they may behave like functions. They may look like functions, right? So that's what a functor is. Okay, they're still class objects. Okay, but with the bracket operator like this, they can behave like functions. Okay, and you can extend the idea to any other operator also, which are not generic functions. This is not the syntax for a function, but you can define it like this. So if we compile this, you see all the expected behavior. So first is 5, and the first one returns n plus 5, so 5 plus 5, 10. Let's see here. The second one, it returns 5, like 5, takes 5, returns plus 4, so 9. The third one, increments increment function, takes 5, increments by 1, and then returns 6. Okay. Right. Okay. So before I think I'll cover this one for sure, and maybe you can continue next class. So lambda 4, because talking about all this, we come to the actual lambda expressions. So some notes about lambda. So lambda expressions look something like this. So first the bracket, which is the capture list. Then the uh, as a square bracket, then the small brackets, which is the parameter list. Spelling is correct. Yeah. Right. And then you have the body with the curly braces. Okay, that is the body. Okay, in between there is a return type also. Yeah. Uh, that's it. So this is the syntax of lambda expressions. Now let's go through each of them one by one. And furthermore, we'll take more examples next session also. But let's try to understand what it is. So what I can do is, right, this is true. Yeah, that's fine. Let's take the main example itself. Now, what I can do is I can use the auto keyword, okay, with some data type return, right? So let's call it print. The capture list does not take anything yet, even the parameter list. Let's worry about the body type. Okay, there is a return type. I'm not going to specify that. Okay, I'll let auto figure it out. So the body will have standard scout as the original hello world expressions and the like. Okay, and I'll end my lambda expression. Okay, this actually needs to be done because you still have a right hand side. So it's like setting a equals to 1, integer a equal to 1, and then you close it. So this is required. What essentially happened now is I have the print function, and this is the lambda expression syntax. Okay, which has the body to print hello world. How to use it? So I'll take print. Okay, use the bracket operation to call the function. So remember, lambda expressions are also functions. Use the bracket operation to call that function, and you can call it as many times you want. Okay, now let's print this and see if everything's working. So 4 times because I called print 4 times. Now, worrying about the return type, there will be certain return type. Maybe it is the cout, maybe auto figures that out. Okay, so now the function itself has a return type. Okay, yes, because that has some data type that is taken care of by the auto. And you can write throw away functions like this. And furthermore, that's why lambda expressions are useful, where you do not need to give a particular name of the to the function, and you want to just have it do something. Okay, maybe it's a very small, minor um, boilerplate kind of code where it's just doing a very small job. So you want to use that function quickly, and then after that, you just want to get rid of it. Okay, so you can do that. Now, what furthermore happens is the syntax looks like this, right? Square bracket, then small brackets, and then curly braces. So curly braces, let's say, still has see out hello world to India. Okay. Now this ends the lambda function, but you can always place extra small braces, right? To actually use that function. So I can end it here. Okay. So if I print this, the extra line also gets printed. So the syntax to use lambda functions is that you have the lambda function. Okay. The extra thing is calling the function using the small brackets. Okay. Now you can put that lambda expression inside some variable name and use that variable name as a function name. Keep using it. You can do that. I'm saying that's the freedom you have. And you have to access that function, you can just use the brackets. Okay. Okay, I think I'll end it here now. Next class, I'll explain more. So this is sort of a very brief intro into lambda expressions. Next class, we covered only body. We'll cover the return type, parameter list, and capture list more. So that's something we left empty, as you see here, right? Okay. So we'll take more examples, and those examples will make clear what all what are all these things, right? And then we'll relate those to these remainder examples that we took before. So I think you can sort of get the idea. This remainder example, I had to write a special uh, function, like I had to define a function to use it. And here I had to use a struct to get sort of the equivalent thing because I wanted to use it. If we see here, remainder uses a function remainder, takes 15. Here it uses I do not want to repeat the word remainder. That's the only reason. But yeah, essentially that's the thing. Remainder takes 15 and also returns. The last line is similar. Okay, it's exactly the same. In, except the name of the called function or functor. Otherwise, they're exactly the same, right? You can use structs, you can use functions directly. How can we do the same thing with lambda expressions? That's what we're going to see. Okay. And yeah, about functors. Remember that it's essentially an object of a class which behaves like a function, like this. Does not mean that it's not a class object. It has its own members, can access them. It can behave very weirdly also because of the very fact that it can behave like a function can be extended to other things also. Okay. And this is the syntax for lambda expression. Okay. So next class we'll see more on this and yeah, other pieces of the syntax of the lambda expression. All right. Okay. That's it. See you guys next time. Next class. Yeah.
One question. So can
Mhm.
we call the functor a method of that class or no?
The founder method of the class. Yeah, you can. I mean, here more specifically, we call the class itself like a functor. The reason being that its objects behave like func here. Its objects behave like a function. The method of the class is actually technically speaking as a that is this small bracket. Yeah, that is the method of the class. Yes. Just so happens that with the normal syntax of looking at functions, this method of the class looks like it's calling a function. Your object is calling a function. Yeah,
Okay.
yeah,
Thank you for the session, sir.
yeah, sure.